In today's class, we will start by looking at an introduction to MOSFETs, their operation and their IV characteristics. So, let us start off with the IV characteristics, because from a circuit's point of view, that is the most basic thing that we require from the device. So, first of all, the MOSFET happens to be a 3-terminal device. It has a gate terminal, it has a drain terminal and a source terminal. And by normal convention for analog circuits, this happens to be the input terminal and this happens to be the output terminal. Now, it so happens that the MOSFET has a gate current, that is an input port current, that is 0, especially at low frequencies, and therefore, there are no input characteristics for the MOSFET. In other words, Ig versus VGS need not be plotted, because it is the gate current is just 0. We will plot ID versus VDS, but now remember that the drain current may be a function of both the drain source voltage and the gate source voltage. So, we will plot in this form. I will put this in brackets, because the basic plot is going to be the drain current versus the drain source voltage, but we will show different curves for different values of the gate source voltage. So, this is your basic plot, and just a reminder that for good amplification, to create a good amplifier using this MOSFET, you want the drain current to be a function of the gate source voltage only, and it should not change with drain source voltage, and therefore, what you desire is straight lines parallel to the x axis. I will show them with different colors to show that there are different values of VGSs. Okay. And so, this is some VGS1, this is VGS2 which is greater than VGS1, and so on. Okay. Now, what does the MOSFET do closer for small VDSs? It so happens that the MOSFET, being a passive device, the IV characteristics have to transition into the third quadrant, especially because Ig is 0. So, I will show the border of this region in this manner using this, but what we are interested in is what happens here, and you will see the MOSFET behaving in this manner. And eventually it will transition into the third quadrant, but we do not have to worry about that for the purposes of these plots. So, this shows the IV characteristics of the MOSFET, and we will note that to use it as an amplifier, we will always use it in this region. In other words, we will use it in the region where the IV characteristics, that the drain current is not a function of the drain source voltage, it is a function of the gate source voltage only. So, now we can go ahead and start writing the current equations of the MOSFET. So, primarily there are 3 separate equations for the current. Of course, the gate current is always 0 for the MOSFET. So, there is no problem with that. Now, if you look at the drain current, there are 3 major regions. So, I will show them like this, maybe I will move this here. First of all, the MOSFET does not conduct if the gate source voltage is smaller than a specific value called the threshold voltage. We will denote that by Vt, V subscript T. Okay. So, if the gate source voltage is smaller than the threshold voltage, the device does not conduct. And now, if the gate source voltage is larger, the device starts to conduct, and now it has two distinct regions. So, the current is given by this expression. So, if the gate source voltage is larger than Vt and the drain source voltage is smaller than Vgs minus Vt, okay, then the drain current has this expression. It is mu n C aux W over L times Vgs minus Vt times Vds minus Vds squared by 2. So, clearly in this region the drain current depends on both the gate source voltage and the drain source voltage, and this represents this region of the device characteristic. The third region is given by the following expression. So, it is half mu n C aux W over L into Vgs minus Vt the whole squared if Vgs is greater than Vt and Vds is larger than Vgs minus Vt. So, clearly if the drain source voltage is larger than the difference between the gate source voltage and the threshold voltage, the drain current is a function of the gate source voltage only, and we are going to use the MOSFET as an amplifier in the third region. This region is called the saturation region of the MOSFET. So, I will show that here. It is called the saturation region of operation, and this region is called the triode region of operation. And as you can see, MOSFET transitions between the triode region and the saturation region depending on the value of the drain source voltage and the gate source voltage. We have seen the behavior of the currents and voltages, we have written down the expressions. So, this nonlinear equation represents the dependence of the drain current on the gate source voltage in the saturation region and will decide the operating point of the MOSFET. And remember, the operating point of the MOSFET is used to calculate the small signal parameters of the MOSFET. This is something you would have learnt in the previous course, the more basic analog circuits course. So, from the operating point, okay, you will derive the small signal or incremental parameters and the small signal model of the MOSFET. So, now let us look at the small signal model. So, if you look at the MOSFET simply as a 2-port, it has 3 terminals, which is the gate, the drain and the source. The gate is the input terminal, the drain is the output terminal, and the source is the common terminal between input and output. And therefore, this can be represented by the small signal y parameters. And note that in the case of the MOSFET, the gate current is 0, which implies that y11, which is dou Ig by dou Vgs, is 0, and y12, which is dou Ig by dou Vds, is also 0, because the gate current is just 0. Similarly, from the drain current expressions, we can derive Y21 as dou ID by dou VGS. Now, Y21 has 3 expressions, we will go ahead and calculate this, but I just wanted to point out that Y22 is dou ID by dou VDS. For an ideal MOSFET, this should be 0, and therefore, in the small signal model, it looks like Y21 is the only significant small signal parameter of interest. So, let us quickly calculate that. Y21 is dou ID by dou VGS in the saturation region. So, let me make a small simplification here to ease the flow of writing. I am going to call this parameter as some beta just to make things easier. So, since these are device parameters and geometric parameters, I can write this as beta over 2 times VGS minus VT the whole square, and therefore, this is nothing but beta into VGS minus VT, which is of course mu n C ox W over L into VGS minus VT. So, this is the first expression for Y21 that we are interested in. Y21 is also called the transconductance or GM Please note that a normal conductance is a single port parameter. So, you talk of resistance and conductance for a 2 terminal 1 port element. In this case, you are talking about conductance referred, the controlling voltage is the input port, but the conductance is seen at the output port, therefore, it is called a transconductance. So, the first expression for GM is mu n C ox W over L into VGS minus VT. Now, from the basic current, this is of course evaluated at the operating point, but now from the basic current equation, you know the relationship between the drain current and the gate source voltage. So, VGS minus VT from the current equation of the MOSFET in saturation is nothing but 2 ID over W over L placed under the square root sign, and therefore, so I will call this expression number 1, and so now from this you can replace the expression for VGS minus VT inside the GM equation. So, you get the second expression for GM into IT. This is, I will call this expression number 2, and now I can also replace the device parameters mu n C ox W over L in terms of the current and voltage of the MOSFET. So, in other words, I can say that mu n C ox W over L is 2 ID over VGS minus VT the whole squared, and therefore, I get the third expression for GM, which is 2 ID over VGS minus VT. This is the third expression for the transconductance of the MOSFET, and of course, all of these are evaluated at the operating point. Now, they are all identical, they are all equivalent. It is just that in some cases you may know the device parameters and VGS and the voltages, so that you can calculate the value of GM. In other cases you may know the drain current directly. In other cases, you may not know the device parameters, but you may know only the drain current and the gate source voltage, and therefore, you should be able to calculate the transconductance of the device. Now, having said this, we have to go back, and I would like to point out that even though we said that for an ideal MOSFET Y22 should be 0, it turns out that for a real MOSFET it is not exactly 0, and it turns out that if you measure the IV characteristics of any MOSFET, even though I will show it for 1 VGS, even though you expect the drain current to be independent of the drain source voltage, the actual drain source voltage will follow the characteristics shown in blue. That is, they will show a slight dependence of drain current on drain source voltage, and for engineering purposes we will represent this as a first order dependence. So, we will say that this is a first order dependence, and we will modify the expression for the drain current in the following way. This is only in the saturation region. So, this was the original expression. We will now add a small dependence on the drain source voltage. Please note that ideally lambda should be 0, but in general lambda should be very small, so that the dependence of the drain current on the drain source voltage is small. Now, what does this mean for us? So, first of all, at the device level, this is something due to it is due to something called channel length modulation. So, that is something you could learn more about in the devices course, in the semiconductor devices course, but for the purposes of this analog ICs course, we will assume that it does have a dependence and it can be modeled as a first order dependence, and we want to find out what implication this has for IC design, for analog IC design. So, therefore, we should see what effect this has on the operating point as well as on the small signal equivalent circuit. So, the first thing we will say, to make things much easier for us, since lambda is very small, we will assume that lambda is equal to 0 only for the operating point calculations. In other words, if you want to find out the drain current for a given gate source voltage, we will assume that lambda is 0, because the lambda is assumed to be quite small, it should not affect your operating point significantly. In that case, why even use a lambda? The reason is, even though it may not affect the operating point calculations, it will still affect the small signal model. So, please note that even though lambda may be assumed to be 0 for the operating point, it can still affect the small signal model of the MOSFET, and let us just quickly see in what way it affects us for the small signal model. So, we have seen so far that Y11 and Y12 are 0 for the MOSFET, and we have seen that Y21 is equal to Gm, and for calculating Gm we will assume that lambda is 0. Okay. So, I will write down the first expression that we wrote down, which is mu n C aux W over L into VGS minus VT. So, the value of Gm does not change, but we still have the fourth parameter, which is y12, which was originally dou id by dou v ds. We had assumed that that was 0, but turns out that is not 0 anymore. So, let us go back and plug in the expression for id. So, it is beta by 2 into Vgs minus Vt the whole squared into 1 plus lambda Vds. This is beta by 2 into Vgs minus Vt the whole squared into lambda. I am sorry, this should be y22 into lambda. So, now we will make one more approximation. Remember that we said lambda is 0 for the operating point, and therefore, we will say that this is approximately equal to lambda times id. Okay. So, the approximation we are making is that the expression for lambda is so small that id can be approximated to this expression alone. So, now this is the conductance between the output ports, and now if you were to find out the resistance, which I will call RDS, which is the drain source resistance of the MOSFET, this is 1 over y22, which is 1 over lambda id. In other words, if you know the lambda for the device and if you know the drain current at the operating point, you can calculate the drain source voltage. So, now we are in a position to draw the small signal model of the MOSFET. So, clearly I am going to take the source terminal as the reference terminal between the input and output ports. At the gate, the device is an open circuit, and on the drain side you have two parameters of interest. One of them is Gm times Vgs. Note that the voltages and currents we are talking about are now the small signal currents and not the total current. So far in the device equations we were writing, they were the DC currents or the total currents. Now we are talking about the small signal currents alone. So, this voltage is Vgs. Apart from this, you also have the drain source resistance RDS, and this voltage is the small signal drain source voltage of the MOSFET. At this point, we need to move ahead and look at some how the MOSFET is constructed in modern ICs. So, we will stop here for this session and start from the MOSFET device geometry from the next class.